This is Lab 2, Motion of a Falling Object. The objective of this lab was to observe and quantify motion as it is changed by gravity as well as drag force. In my experiment, my friend John dropped a tortilla warming sleeve, which is in the shape of a circle, and it was seen that the model that was created through Python effectively predicted the motion of the tortilla warming sleeve as it was compared with the data in Tracker. So, in order to observe the effects of gravity and drag force, computational models were created with only gravity and then with gravity and drag force. By applying Newton's second law, one can understand how the principles of physics are applied to this case. As in Lab 1, the observed motion was analyzed in Tracker and the computer model was created in VIDLE, and the data was compared to observe the differences in the outcomes of each model. Newton's second law, or force equals mass times acceleration, is applicable in this lab. Newton's first law cannot be used because it describes the principle that an object in motion stays in motion unless acted upon by a force. In this case, the Earth is acting on the object through gravity, and we must account for the drag force as well. By breaking down Newton's second law, we can arrive at the equation V final equals V initial plus F net divided by mass times delta t. In this case, the initial velocity and the final velocity are not the same, so we can assume that F net must not be equal to 0. Thus, at least one agent in the surroundings is exerting a force on the system in order to make it accelerate in the negative y direction. Here's the video of the tortilla warming sleeve. The tortilla warming sleeve is the system and everything else is the surroundings. I marked the center of the mass for the object by eye in each frame. In several frames the object was blurred, so I marked the center of the blur as the best estimate for the center of the mass, or the average position of the object. The final time of observation was time equals 0.633 seconds. I chose the positive y direction to be up and the negative y to be down. The final position was measured at negative 0.78 meters. Taking the data that was collected by Tracker, I put the initial values into the code given us in the start of the lab. I used the first two time points and their respective positions to find the initial velocity, and to calculate the final velocity I used the final two time and position points. The start frame was 45 and the end frame was 65, and the camera recorded at a rate of 30 frames per second. The mass of the tortilla sleeve was 0.009 kilograms. After running the code, the blue arrow is the drag and the yellow is the force of gravity. The object was calibrated to the length of the light switch cover at 0.13 meters. One agent that is acting on the object is the Earth, which exerts a weight force on the object and is calculated by the equation weight equals negative mg j hat. So a computational model can be created under the assumption that this is the only force acting on the object. As you can see, the model with only gravity is over-predicting the position of the object, or assuming that it fell much quicker than the observed data shows. This is because you have to add the drag force into the equation, which is a force in the opposite direction of the weight force. In order to calculate the drag force, you must use the equation Fd equals negative b times the magnitude of the ball velocity squared times v hat. You can see this in my code here. V hat was set to 0, 1, 0 to show the direction of the drag force to be in the positive y direction. To find the proportionality constant b, I ran the model several times until the printed final position matched the observed final position, negative 0.78 meters. The net force, as seen in the code, is now equal to the weight force plus the drag force, whereas before the net force only accounted for the weight force. I also adjusted the arrow scale of the model so that the model represents the motion correctly. At first, the drag force is negligible because it is dependent on the object's speed. As the object speeds up, the drag force increases and begins to affect the motion. As you can see, after adding both forces, the model predicts the motion of the experiment much more effectively. You can see the model here that accounts for gravity and drag in the orange. Now to the questions. What does it mean? The second model, which accounts for both gravity and drag force, much more effectively moves towards the terminal velocity. You can see this through the velocity versus time models. This is the model for just the gravity, and this is the model using both forces. While neither reaches the terminal velocity, the velocity versus time with drag and gravity much more effectively moves toward the terminal velocity, but because the time of observation was nearly 0.633 seconds, it did not have enough time to reach the actual terminal velocity. Now for the what if. The terminal velocity will be the same if the object is thrown down, and will be reached at approximately the same time. The difference is if the initial velocity of the object exceeds -10 meters per second, then it would have to first decelerate. Then the net force would become 0 and the terminal velocity would be reached. Thank you for watching.